Through the work of lots of scientists, including people like J.J. Thomson, who had an initial idea for the atom, which was later debunked, as well as Marie Curie, who did a lot of work with radioactivity, they came up with this kind of model of the atom. And this did not happen overnight. It took lots of iterations, some trials and errors. But what they found, and what the current model proposes, is that atoms contain three types of major particles called protons, neutrons, and electrons. And the protons and neutrons are in the nucleus, in the center of the atom, and electrons are on the outside, that kind of shimmering stuff you see around the nucleus. Also important is that the glue that holds the atom together is basically around positive protons and negative electrons. Positive and negative charges attract each other, which is important, and that's one of the main things that holds the atom together. Neutrons are neutral. They have no charge at all. This is an overview of some exact values for protons, electrons, and neutrons. So protons are positive, and in science, charge is measured in what's called a coulomb. It gets the symbol capital C. And they've determined that one proton has a charge of 1.6 times 10 to the minus 19th coulombs. And that's a very small number under any scale, but it does represent the positive charge that's on a proton. Now, they've also been able to figure out the mass of a proton, and it's, again, very, very small, 1.67 times 10 to the minus 24 grams. Now, using a number like that is very unwieldy. So if you take that number and you divide it by the AMU, you get a relative mass of what's called 1.0073 AMUs. So this is just a little, the proton is just a little bit more than 1 AMU when it comes to the mass. So if you put it on a scale, an AMU scale, it would be just a little bit more than 1, and that'll be important for something coming up. Electrons are negative. So you can see the charge on the electron there, minus 1.6 times 10 to the minus 19th coulombs. So they're the same magnitude, but opposite charge. Protons are positive, electrons are negative. Now there's the relative mass of an electron, and you'll notice it's really, really small, 0.0005. So it takes hardly any mass and stuff to make up an electron. So while a proton is small, electrons are really, really small, much, much, much smaller than the protons that they come from. A neutron, on the other hand, has no charge, so there's no coulombs associated with it because it's not positive or negative. It would have a charge of 0 coulombs, I suppose. And the mass is 1.0087 AMUs. So you can see how, of the three particles, the neutron is the biggest. 1.0087 is bigger than 1.0073 for the proton. But both neutrons and protons are about the same mass. Neutrons are a little bit bigger, but they're about the same mass. And they're much bigger than the electron, which is 0.005486. So if you put these all on a scale, protons and neutrons would be about the same, and electrons would be much, much, much less than that. Here's the kind of question to see how you're doing with this information. It says place the three subatomic particles in order of increasing mass, so from the smallest to the biggest. And like we talked about in the last part there, the electron is much, much, much smaller than the proton and neutron, so it's going to be the smallest. It'll go first. And although protons and neutrons are both about 1 AMU, the neutron is a little bit bigger than the proton, so the best answer here would be answer D. Electron is smaller than a proton, and a proton is a little bit smaller than a neutron.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Rutherford is a fantastic scientist, and I could go a long time talking about how cool he is. But anyway, Rutherford actually came from New Zealand, and he went to England to study. And at the time, they thought that people from the colonies were inferior and not really worthy. But Rutherford worked really hard, and he came up with this idea for the gold foil experiment, which is still just an experiment that has rocked the chemistry world for a long time. And in that video, you could see how most of the alpha particles, which is a type of radiation, just went right on through. All right, no big deal. And everybody kind of thought that was going to be the case. They thought that atoms were big kind of amorphous things, and most of the time the radiation would go through. But sometimes the little alpha particles would reflect back, and they would go back and hit that kind of photographic plate around it. Sometimes they'd go off to the left or the right. And so, long story short, they realized that the atom must be very dense and very positive. And here's why. Alpha particles have a positive charge. And if the density of the highly dense nucleus is positive as well, then positive and positive is going to repel. So some of those alpha particles came back and kind of went to the left and the right. And some of them kind of reflected off to the left and the right, or refracted, I guess would be a better term. Anyway, it was a fantastic experiment, and nobody saw this coming. And scientists still talk about this today. So the gold foil experiment is Rutherford's big thing. And he discovered how the atom is actually very, very dense in the nucleus, and it has a positive charge. But most of the atom is quite empty. Here's another graphic kind of showing what's happening. So what happened, what Rutherford's results were here, is that in the left-hand side, the nucleus itself is incredibly small, all right? Like they feel that the atom is roughly, you can see there, 10 to the minus 10 meters across. So that would be the diameter. But if you look down on the kind of middle right, the nucleus itself, 10 to the minus 15 meters. So what that means is the nucleus is incredibly small. All right. And if it's incredibly small with all those protons and neutrons, which, by the way, have a lot more mass than the electrons, man, that thing is going to be super dense, and it's going to be positively charged because of the protons. So then in this upper part, the alpha particles are coming through like this. And again, remember, alpha particles have a positive charge. And most of them just go straight on through. No problem. They don't care at all. But boy, once in a while, when they get next to the nucleus, that's when they kind of go up and to the left, or some of them came back like that to the right if they had a direct collision. Nobody saw this was going to happen. So Rutherford's gold foil experiment still defines how scientists think of the atom. It's just that nucleus super dense, super small, electrons float around the outside, so most of the atom is empty, but oh boy, if you get to that middle nucleus, things start to happen. Most of the atom is empty space, protons and neutrons in the nucleus, and that nucleus is very, very dense. Electrons are in space around the nucleus. Now, here's another important concept. If you have an equal number of protons which are positive and electrons which are negative, the atom overall does not have a charge, and the atom is electrically neutral, all right? We're going to talk more about this later, but if the protons and electrons are equal, then we consider the atom to be neutral. Like it doesn't have a net positive charge if you have an excess of protons, or a net negative charge if you have an excess of electrons. And boy, oh boy, are these atoms small. And in the chapter 1 introduction, I talked about how a teaspoon of water has just a ton more molecules than there are teaspoons in the Atlantic Ocean. Well, because water is H2O, 2 hydrogens, 1 oxygen, 3 atoms, you can even say that this 1 teaspoon of water has 3 times as many atoms as the Atlantic Ocean has teaspoons of water. So just really small. All right, you can't get out your photographic equipment normally and take pictures of these things because they're so small. You need special techniques. Pretty cool stuff.
It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol.
I love these old science videos, but I like the idea here. If the atom was the size of the United States, then the nucleus would be 100 feet. So, wow, pretty small. Anyway, just kind of putting in perspective there. Kind of cool. Here's a picture of 35 xenon atoms. IBM has been a real leader in trying to have pictures taken of atoms. And if you use your imagination there's an I on the far left, a B kind of in the middle, and an M and there on the right. And to manipulate individual atoms like that is pretty fantastic. They used to take this picture what's called scanning tunneling microscopy, STM. That's just one example of some of these new techniques that are being used to measure and take pictures of atoms. And there you can actually find on the internet little movies and stuff of them using atoms to move things around, which is cool. There's a website down there. If you're curious, you can look up more information on how IBM does STM to see atoms. But again, think about how small those are, because each of those little humps, those little mountains, if you will, is about 10 to the minus 10 meters, which is what scientists sometimes refer to as an angstrom. The A with the circle on top is an angstrom. But the nucleus would be basically 5 orders of magnitude smaller, 10 to the minus 15th meters. We don't have cool pictures of that because that's still so small. But hey, we're at the atom, so maybe one day. I'm hopeful anyway.